talk about conjectures and counterexamples, which we're going to do in the form of analyzing patterns to predict the next term in the sequence. So let's try some easy ones. Take a look at the numbers in this sequence and see if you can figure out what number comes next. If you said 48, you're correct. What we're doing in this sequence is just doubling. We're multiplying by 2. 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24, so that means I would multiply 24 by 2 to get to my answer of 48. Let's try another one. This one's a little bit more challenging. You might think at first that we're adding. 9 plus something is 16, that would be 9 plus 7. And then if I add 7 to 16, well, that doesn't get me to 25. So I'm not just adding the same thing each time, and I'm not multiplying, because what do you even multiply 9 by to get to 16? So what is going on here? Well, sometimes you have to look for more than just adding or subtracting or multiplying or dividing. There's other types of special numbers as well. These are actually what we call perfect squares. 9 is 3 squared. 16 is 4 squared. 25 is 5 squared. 36 is 6 squared. And 49 is 7 squared. So it's just 3, 4, 5, 6, 7 squared. So the next answer would be 8 squared, which is 64. But you might be saying, well, wait a second, that's not how I did it. I did it with addition. Well, that's a possibility. Let's take a look. You're still going to get to an answer of 64, but not because you're adding 7 every time, but rather because there's a pattern in what you add. To get from 9 to 16, I added 7. To get from 16 to 25, I added 9. And then I added 11. And then I added 13. These are just the next odd number in line. So after 13, the next odd number would be 15, and yeah, 49 plus 15 gives me that same answer of 64. So sometimes there's going to be more than one correct explanation, more than one correct conjecture to describe what's happening in a pattern. Let's try a pattern that's shapes instead of numbers. What shape would come next? If you said a hexagon, you're correct. All we're doing is just adding an extra side. Triangles have 3 sides. Squares have 4 sides, pentagons have 5 sides, 3, 4, 5, the next thing would be 6, so a hexagon. What about this one? It's way more complicated than just adding an extra side to a shape. What's going on here? Well, sometimes it's easiest to figure out what do they have in common from each shape to the next. I see that they're all circles with a vertical line and a horizontal line. Circle, vertical, horizontal. Circle, vertical, horizontal. So I know that my answer is going to have to be a circle with a vertical line and a horizontal line. So really what I'm trying to figure out is what's going on with the gray square and the black triangle. Well, I see that all of my terms have one of each, so I'm going to end up with a gray square and a black triangle in my answer. I just have to figure out which quarter of the pie it's going to end up in. Well, let's just track it one at a time. The black triangle started in the top right corner, and then it moved to the bottom right corner, and then to the bottom left corner. It's almost like it's rotating. It started in top right, then it went to bottom right, then it went to bottom left. So I think in my answer I'm going to end up with a black triangle in the top left corner. Well, let's look at the gray square. The gray square started in the bottom left, and then it went to the top left, and then to the top right. So this is rotating as well. It started bottom left, went to top left, went to top right. So it looks like a gray square should be in the bottom right corner of my answer. And yeah, that's what I ended up with. I've got, well, not black because it turned red, but I've got a dark triangle in the top left-hand corner, which makes sense because the triangle was rotating around. And I've got a light-colored square in the bottom right-hand corner, because the gray square was rotating around as well. So really, all we're doing for this is rotating the entire shape 90 degrees clockwise. What we just did on each of those 4 warm-up activities was write a conjecture. A conjecture is basically just a description of what you see in a pattern. It's an unproven statement based on observations. It's another word for educated guess. And the other thing that we'll be talking about in today's lesson is something that you should already be a little bit familiar with from our previous 2 lessons, and that's the word counterexample. A counterexample is something that demonstrates a conjecture is false. And again, a conjecture may be words or it may be a diagram. So let's take a look at some more patterns and see if we can figure out the next term and write a conjecture to describe what we see. 30, 28, 26, 24. Well, it looks like I'm just subtracting by 2 each time. So the next term would be 22. And for my conjecture, I'm just going to write a sentence to describe how I got from one term to the next. Something like, for this pattern, we subtracted 2 to get to the next term. Simple enough. Let's try another one. 5, negative 10, 20, negative 40, 80, negative 160. Well, if I just forgot about the negatives, it looks like I'm doubling, right? 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40, and so on. I'm just doubling. But how do I make it change its sign each time? Well, instead of just multiplying by a positive 2, if I multiplied by negative 2, wouldn't that cause the change in signs that I see? 5 times negative 2 is negative 10. Negative 10 times negative 2 is positive 20. Positive 20 times negative 2 is negative 40, and so on. So to get to my next term, I'm going to multiply by negative 2. And negative 2 times negative 160, that's a negative times a negative, so I get a positive 320 for the next term. And my conjecture would be that I'm multiplying by negative 2. Let's try another pattern of shapes. All of the terms in this sequence look like little pyramids made out of circles. The first pyramid is 2 rows, the bottom row has 2 dots, and the top row has 1. The next term in the pattern has 3 rows. The bottom row has 3 dots, the middle row has 2, and the top row has 1. So it's actually kind of like the first term, except I have an extra row on the bottom. And then the next term is 4 rows instead of just 3, and I start out with 4 dots on the bottom. And then 3 dots on the next row, 2 dots on the one after that, and then 1 on the top. So again, it's kind of like the previous term, just with an extra row underneath. So then for my next term, my answer, wouldn't I just take what I have here, this 4-row pyramid, and add another row underneath of it, but I also have to add an extra dot to that row. This bottom row had 2, this bottom row had 3, this bottom row had 4, so that means that my answer bottom row has to have 5. So I have a row of 5, a row of 4, a row of 3, a row of 2, and a row of 1, a total of 5 rows. Okay, well that probably makes sense visually, but how do I describe that in words? You need to be as specific as possible, because if you just say, I added a row, well, you added a row to what? And that row, what does it look like? You have to be more specific than just add a row. It's almost like you have to write a conjecture as if you're describing it to someone who can't even see the pattern. Like you're describing the pattern to someone over the phone. They can't see what you're talking about. You have to describe it for them. So for this conjecture, I might write something like, we add a row that contains 1 extra circle to the bottom row of the pyramid. So this conjecture describes that we're making a pyramid, it's made out of circles, and to get from one row to the next, you have to add an extra row that has 1 extra circle. If you were to describe that to somebody over the phone, I think they would be able to get to the next row, which would have 6 dots on the bottom and a total of 6 rows. Let's try another one. It might be hard to describe in words, but can you imagine in your mind what the next term would look like? I started with just an empty square, and then I had a square with another square inside of it, except it's more like a diamond instead of a square. And then I had a square with a diamond inside of it, with another square inside of it. So what's my next term going to look like? Well, I would have to add another diamond inside. So how am I going to describe that for my conjecture? I might say something like this. We add an extra square to the center of the shape. But that's not enough, right? Because if I was just adding squares, I wouldn't have a diamond instead of a square. So we're going to need to add some extra information that says that the square has actually been rotated and it's 45 degrees. If you don't know off the top of your head that that's a 45-degree rotation, don't worry, we'll talk about that some more later in the year. For that situation, you could probably just say it's rotated into a diamond instead of a square, but you still have to add that extra description of not only are you adding a square to the center of the square, but the square that you're adding is rotated compared to the square that it was being added to. All right, get your calculator out and let's do some explorations with math. Type each of these problems into your calculator. What's 101 times 26? 101 times 33? What do you get for each of these? Pause the video and explore the pattern to see if you discover anything. 101 times 26 is 2626. 101 times 33 is 3333. 101 times 54 is 5454. 101 times 87 is 8787. Do you see a pattern in our results here? Okay, well now your challenge is describe it. Write a conjecture that describes what you discovered. Well, what were we doing each time? We had 101 each time. That was the same for all the problems. And then we multiplied it by a number. Okay, so that's like the first half of my conjecture. We're kind of going to write a conditional statement. If I do something, then I'll get a certain result. So let's concentrate on the hypothesis first. What am I doing each time? I'm multiplying 101 times a number. Okay, so if I multiply 101 times a number, what's my conclusion? What do I get out of that? How do you describe what these answers look like in relationship to your hypothesis? Well, you might say something like this. If a number is multiplied by 101, that was our hypothesis, then the product, remember product is what you get for your answer when you multiply, will be a 4-digit number whose first 2 digits and last 2 digits are the number that 101 was multiplied by. Well, that's a pretty good conjecture. But could you provide a counterexample for it? Play around with your calculator, multiplying 101 times any number that you can think of. Can you break the pattern? Well, what if you were to multiply 101 by 123? We would expect it to be 1, 2, 3, 1, 2, 3, right? Based on what we saw on our explorations at the beginning, it looks like if you multiply 101 times a number, then you get that number twice. But you don't. If you multiply 123 by 101, you get 1, 2, 4, 2, 3. That breaks the pattern. That didn't work. So we need to rewrite our conjecture. We need to add a little bit of extra information to it to make it more specific. Your goal with every conjecture is to make it so that you can't provide a counterexample. So let's rewrite our conjecture to include the words 2-digit. If a 2-digit number is multiplied by 101, then the product will be a 4-digit number whose first 2 digits are blah, blah, blah. That part stayed the same. All that we changed was that the number that you're multiplying 101 by has to be 2 digits. It has to be like the numbers that we first explored. If you multiply by something that's 3 digits or 1 digit or 10 digits, it's not going to work anymore. This is the kind of conjecture that you should strive to write because you can't provide a counterexample for it. Let's try another one. 2 times 1.1, 4 times 1.1, 7 times 1.1, 8 times 1.1. What do you get when you multiply each of these? You get 2.2, 4.4, 7.7, 8.8. So let's write a conjecture to describe this. First, I have to say my hypothesis. What am I doing each time? Well, it looks like I've got 1.1 for all of them. So if I multiply 1.1 times a number, okay, so that's my hypothesis. Then what do I get as a result? How do you describe what happened here in relationship to your hypothesis? Well, it looks like we got the same number that we multiplied 1.1 by, but we got it twice, with a decimal in between. So let's write that out as a conjecture. If a number is multiplied by 1.1, the product will be a number whose ones digit and whose tenths digit are both the number that 1.1 was multiplied by. Now, I use my fancy math words like tenths digit. If you had described it more like, if I multiply 1.1 by a number, then I get that number in front of the decimal and behind the decimal, that would be okay as well. I don't expect you to be a mathematician, but I do expect you to use as precise of language as possible. So if you just say that I multiplied 1.1 by a number and I got that number twice, well, that's not quite good enough, right? Because if you got that number twice, then it would have been 22 and 77. You have to mention somewhere in there that there's a decimal, or reference exactly which digits are which. But again, could you provide a counterexample for what we just wrote? In order to find a counterexample, really you just have to keep playing around with the pattern. Keep trying to discover ways to break the pattern. For example, what if I multiplied by something that wasn't just one digit? Everything I multiplied by in my original pattern, 2, 4, 7, and 8, those were all just one-digit numbers. They were all less than 10. But if I multiply 1.1 by something that's 2 digits, well, according to my conjecture, I should get 18.18, but I don't. I get 19.8. So a 2-digit number breaks this pattern. A better way to write my conjecture then, it would be to say that if a 1-digit number is multiplied by 1.1, then the product will be a number whose yada yada, the rest of it stayed the same. So oftentimes you don't have to add a whole bunch of extra information to your conjecture to make it unable to be proven false. This little addition right here is all that I needed to add to make this a good quality conjecture. Alright, you're on your own for this next one. Play around with this pattern and write a conjecture for it. And once you've written your conjecture, look it over. Play around with the pattern some more and see if you can break your conjecture. See if you can provide a counterexample. And if you can, go back to your conjecture and rewrite it to make it more specific so that you can't provide a counterexample. Pause the video and try it now. Let's see how you did. Well, hopefully you didn't even need a calculator to solve these, right? If I multiply 7 by 100, I get 700. 18 by 100, I get 1800. 53 times 100 is 5300, and, well, 144 times 100 isn't 14400 per se. We would say that's 14,400, but you get the point. So you might have made a conjecture that looks something like this. If you multiply any number by 100, the product will be a number whose first digits are the number that 100 was multiplied by, and the last 2 digits will be zeros. But can you find a counterexample if your conjecture looked like mine, if it wasn't specific enough? Mine, the way that I have it right now, is not quite good enough because this pattern doesn't work for decimals. You would expect this to be 18,500, but because it has a decimal, it actually is just 1850. So I'm going to reword my conjecture to say if you multiply an integer by 100. Integer is a really good word to know if you don't already know it. Integer is the fancy math way of saying a pretty number. Integers are things that don't have a fraction component or a decimal component. So 18.5, for example, is not an integer because it has a decimal component. Whereas 100 is an integer, 1850 is an integer. And all of these that I multiplied by in the beginning, they were all integers as well. That's why the pattern worked for them. So just by adding this one extra word of integer, that alone was enough to make my conjecture unable to be proven false. So let's try some examples where you're not given the pattern to explore. Instead, the pattern is described to you, and you'll have to make up your own examples. Let's take a look. The sum of any two odd numbers will be, and then you're supposed to write a conjecture off of that. And you're like, well, what does that even mean? Well, let's do what it's asking us to do. Sum means addition. 2 means two things. And odd numbers. Well, odd numbers are like 3, 5, 7, 19, 31. all of those numbers that aren't divisible by 2. Those are all odd. So they want us to add 2 odd numbers. Well, let's just pick any 2 odd numbers and see what we get. So for example, I could do 1 plus 3. 1 is odd, 3 is odd. I'm adding them, so my answer is a sum. There's 2 of them. Okay, looks like I'm matching my pattern that was described to me. And I got an answer of 4. Well, just looking at one example really isn't enough for you to be able to write a conjecture. We need to explore the pattern and see if we notice anything about it. So let's keep going. 15 and 27, those are both odd numbers. And if I add them together, I get 32. Okay, what about, well, it didn't say I couldn't do negative numbers. Why not do a negative odd number? Negative 9 plus 11, that's 2. Are you starting to notice anything in common about our answers that we get when we add 2 odd numbers? If not, then keep adding odd numbers together until you do notice a pattern amongst your answers. But maybe by now you already saw it. All of our answers so far have been even. The sum of any 2 odd numbers will be an even number. And no matter how many of these examples you come up with, you'll never be able to prove that wrong. That's actually just a fact. There is no counterexample that can be provided because it's true. The sum of any 2 odd numbers will be an even number. Well, let's get some more practice of proving things wrong. Here's a statement, and we need to come up with a counterexample for it. It says the sum of 2 numbers is always greater than both of the numbers that were added together. So some examples of that would be 1 plus 3 is 4, right? 4 is bigger than 1 and 4 is bigger than 3. So that's an example of this conjecture that we've been provided. Or if I do 100 plus 100, that's 200, and 200 is bigger than 100, so that's another example. Can you come up with a counterexample, though? That if I added 2 numbers together, the answer that I got, the sum, would be less than one of the numbers. What would have to be true about one of the numbers in order to make that happen? What if one of the numbers was negative? For example, if I add 2 and negative 9, I get an answer of negative 7. But negative 7 is not bigger than 2. So for your counterexample here, you can do one of the 2 things, or both, that I have up here on the screen. You can either describe in words what would make it not true, or you can give an example that shows why it's not true. Either one would be counted as a counterexample. Let's try another one. The square of a number is always larger than that number. Well, remember, square means that you have the little 2 in the air, right? That you're multiplying it by itself, like 3 squared is 9. Well, and that's an example of this. 3 squared equals 9. 9 is bigger than 3 was, so that's an example. Or like 5 squared is 25. 25 is bigger than 5, so that's an example. But I want a counterexample. I want something that, if I square it, I actually end up with a smaller number. Can you think of anything? You might think negative numbers at first, because negative numbers do often break a pattern. But if I square negative 6 times negative 6 is positive 36, so that's still just another example, because 36 is bigger than negative 6. So what else do you got? What about a decimal? If you square a fraction or a decimal, specifically a fraction or a decimal that's less than 1, then you get an answer that's actually smaller than what you started with. For example, if you square a half, you get a quarter. 0.5 squared is 0.25. And 0.25 is smaller than 0.5, so that breaks the pattern. And our last example takes us back to either Algebra 1 or 8th grade for a second. With absolute values, that's what those bars around the x is, given an equation of the form the absolute value of x equals a, where a is any real number, the equation will have 2 solutions. Well, what does that mean? Let's think of some examples first. If I plug in 4 for a, what could my answer for x be? Well, since absolute values make things positive, x could be positive 4. The absolute value of 4 is 4. But x could also be negative 4, because the absolute value of negative 4 is positive 4. So that's an example. The equation has two solutions. If I want an answer of 4, I could either plug in positive 4 or negative 4 to get that answer. So could you think of something that if you plug in a number for a, you can only get one value of x that works? Well, there's a couple different options. One is negative numbers, because the absolute value of a number can never be negative. If you make a negative number, then the answer to the equation is that there is no answer. Absolute values set equal to a negative number, that kind of an equation has no solution, not two solutions. So that'd be a great counterexample. But another example might be 0, because the absolute value of 0 is just 0. Not negative 0 and positive 0. I don't have two versions of 0 like all of the other numbers. 0 is just 0. So instead of having two solutions, if you make a equal to 0, then it has just one solution. And that's all you need to know about conjectures and counterexamples. In our next lesson, we're going to write our very first proofs, but they will be easy because they're just algebraic proofs. Which is to say that you're basically just going to solve equations.